Hello everyone, I am Vaishnavi Lahare from Tiva Electrical. Along with my group members, we are here presenting the topic of Nyguist stability criterion under the guidance of Dr. G. Vijay Kumar sir. So let's understand the concept of the Nyguist stability criterion. The Nyquist stability criterion is a graphical method developed by Harry Nyquist in 1932. It helps us determine whether a closed loop system is stable by observing its open loop frequency response. Instead of solving complex characteristics equation, Nyquist provided a way to understand system stability visually. We plot the frequency response on a complex plane. This is called the Nyquist plot. The most important thing we observe is how this plot behave around a critical point at a -1, 0. Stability is judged based on how many times and in what direction the plot encircles this critical point. Now, what exactly is the Nyquist stability criterion? It gives us a direct connection between the open loop behavior and the closed loop stability. When we create the Nyquist plot, we map the function g of s, h of s as it travels along the imaginary axis. The rule is simple but powerful. If the number of clockwise encirclements of the point is -1, -1 is equal to the number of the poles of the open loop system is the right half of the S-plane. The system will be stable, otherwise it will be the unstable. This method is extremely useful, especially when dealing with systems that behave time delays or the complemented dynamics where algebraic analysis becomes difficult. By simply analyzing the shape and encirclements of the plot, we can easily predict stability without solving the high-order equation. According to the Nyquist stability criterion, the number of clockwise encirclements of the point is -1. -1 must match the number of poles of g of s, h of s that are in the right half of the S-plane. If the condition is satisfied, the closed loop system is stable. If not, the system will unstable. This method makes it very easy to judge stability, especially when dealing the complex system.
I'm going to explain Nyquist stability criteria program in MATLAB. First of all, we have to define the transfer function g of s into h of s. Here it is the example is taken g of s into h of s is equals to 1 upon s square plus 3s plus 2. Here we are going to define the numerator coefficient as 1, then denominator coefficient as denominator is equals to 1 comma 3 comma 2, then system is equals to transfer function num comma denominator to create the transfer function. Here num is the numerator of g of s into h of s. Here it's just 1, denominator is the s square plus 3s plus 2. Then it after that system is equal to transfer num comma denominator. It creates a transfer function object in MATLAB for g of s into h of s. So the transfer function is g of s into h of s is equals to 1 upon s square plus 3s plus 2. Here in the second part, we have to plot the Nyquist diagram. So for plotting, we are using MATLAB figure semicolon Nyquist system semicolon title Nyquist plot of this function g of s into h of s, then grid on, then opens a new figure window, a Nyquist system, plots the Nyquist plot of transfer function. Then we have to add the title and grid to the plot. The Nyquist plot is a graph of the frequency response. And after that, we are going to extract the Nyquist plot data for analysis, in which MATLAB n comma d is equals to Nyquist system equals to real part. Then we have to squeeze the remove squeeze means we have to remove unnecessary singleton dimension to make real part and imaginary part into simple 1D arrays. Here in Nyquist system can return data if you request output variables. Here n contains real and imaginary part. After squeezing, real part is plot on the real axis values of the Nyquist curve, and imaginary is the imaginary values which are plot on the y-axis. Then we have to mark the critical points -1 comma 0. For that, The program is MATLAB. Hold on. Plot -1, 0 rx marker size, 10, line width, 2. Here hold on allows plotting additional items without deleting the existing Nyquist curve. Then after plot -1, 0 rx and so on. Here plot red x denotes at the critical point -1, 0. In applying the Nyquist criteria is to identify the critical point at -1, 0 in the complex plane. This point is manually plotted as red x on the Nyquist plot to visually indicate where the system stability is judged.
The number of encirclement programmatically the code examining the data points of the Nyquist plot. It iterates through each pair of consecutive points and to check the two condition. First, whether the real part of the curve crosses the vertical line at -1, meaning the real value goes from less than -1 to greater than -1, and the second, whether the imaginary part of this point have opposite sign, indicate that the curve crosses the real axis. When both conditions are satisfied, it is considered one encirclement and the counter encirclements is increased. Finally, the number of encirclement is used to determine stability. If there are zero encirclement, it indicates that the closed loop system has no unstable poles, and thus the system is stable. If there are one or more encirclements around the critical point, the system is declared unstable. This program assumes that the open loop system has no poles in the right half of the S plane, which is correct in the case because the pole at -1 and -2 are both in the left half plane. Therefore, according to the Nyquist stability criterion, the number of encirclement directly tell us about the system's stability. To check the encirclement, we have taken for loop. In for loop, we have taken the condition k is equal to 1 as to length real part -1. So after that, we are taking if condition in which a real part k less than -1, a real part k plus 1 greater than -1. So imaginary part k, encirclement is equal to encirclement plus 1. Then in we have to determine whether it is stable or not. For that, we are using a stability decision. The we are using if condition, the using encirclement is equal to 0. Then we have to display whether system is stable according to the Nyquist criterion. If not, then use else, display system is unstable.
Here, the basic idea of Nyquist stability criteria. We look at the how the plot encirclement and critical point, which is -1 plus j0. That's at -1 on the real axis. You count how many times and in what direction, clockwise or anti-clockwise, the plots encircle the point. Based on this, the knowledge how many poles and open loop system are in the right half of the complex plane. You can predict if closed loop system is stable. In simple words, if the system encircles the critical point in the right number of times according to rule, the system is stable. If not, it's unstable. The formula of this is n equals to p minus z, where n is the number of clockwise encirclement, p is the number of poles of the open loop transfer function and right half plane, and z is number of zeros in stable poles of the closed loop system in the right half phase. And for understanding this plot, the step one is the this Nyquist plot of open loop transfer function. The x-axis shows the real part and y-axis shows how the imaginary part. Second step is identify critical points. The Nyquist analysis, the important point is on real axis. We can check the curve is encircled this at this point. The third one is check the plot encirclement. In our plot, the blue curve does not circle the point. It says that to right, below, or above, but never arms around it. And step 4 is apply Nyquist stability criteria. If P is equals to 0, and dn is equals to 0, and z is also equals to 0. Thank you.